I would. So Gael, whenever you're ready.
Okay. So you should see my screen.
Looks good.
Okay. So getting back to direct imaging for young planets. So here for this first slide, what I wanted to summarize, as highlights for almost like 20 years of, discovery characterizations. I think there are like kind of 5. I think the first one it has been, of course, described by Anne-Marie. I think it's really related to the development of like instrumentations for higher angular resolutions and high contrast. And more than instrumentation, also the data processing. So, we have been starting in Palomar, already, in 1994 with the first detection of substellar companions, and then progressing, towards, the developments of the techniques that you're combining. And now we're reaching typical contrast, of 10 to minus 6 at like 300 to 500 milliarcseconds with these combinations from the grounds of large telescopes, adaptive optics, coronagraphy, differential imaging, and now we're even pushing, with the combinations of like a medium to high resolution spectrograph. And this is what you need to actually detect, like I would say, 2 to 3 Jupiter mass planets at, let's say, like 10 to 20 astronomical units around a classical young nearby stars. And this is, of course, for emitted light. I think the second aspect, of course, is thanks to the stability, the improvement of these instrumentations. The first amazing results we got, with GPI and Sphere, and thanks to the stability of the instrument, it's really this kind of amazing images of the planet-forming disk with a lot of structures, spirals, gaps, vortices, clearly indicating that you have processes at play and probably planets that are just forming. If then you go a bit like to systems which are a bit older, so you go to what we call the debris disk stage, then clearly you can identify the planets. So it's what you see with the HG95086 system. You have the planets, so that was actually imaged with NECO and then also monitored with GPI and Sphere. But what you have also, you have additional informations here from ALMA, and you see that you have this multi-belt architecture. So we can monitor the orbits of the planets, and then we can also study actually the full dynamical stability of the planets itself, of the multi-belts that you have. And you see that for various systems that we have actually detected, like HR799, BetaPIC, HG95086, we have this kind of architecture which is very similar to what we have in our solar systems. These belts, giant planets, and so we can see that in the inner part you might even have this telluric planets that are just forming. A fourth aspect is really related to the planet itself, and you can just you have the light, so you can characterize the planets, so you can get the spectrum. 10 years ago we had only photometric data points, and now with like the new generation of planet imager, we have this like amazing low resolution spectra, like this one for 51 Eridani B. So you can with that start to get like good constraints on the bulk properties of the giant planets. So effective temperature, surface gravity, informations on the composition. And now what we're doing, we're trying to push on the spectral informations, by pushing the spectral resolution. So going to low to medium resolution spectrograph to high resolution spectroscopy to get more information on the diversity of the atmosphere. For instance, like measurements of the molecular abundances, isotopologs, for instance, and to try to connect that to the formations of the planet itself. The last part is more related to the demographics, was presented by Anne-Marie. Of course, here it's like you take all the information you have for a large survey, the number of detection, and then you just put a number on the occurrence of giant planets that you find. And this is really critical in a way, just to feed the predictions of population synthesis models, what you have seen yesterday, and just to see how the models fits with the observations. And this is really time consuming, but this is really important, really to try to constrain the predictions of theories of planetary formation. Okay, so now switching to the open questions. So of course there are many. I've decided to select like 3 categories. The one is more related to the formation and evolution. So okay, we got like the first discovery of giant planets something like 25 years ago. But still, with all these discoveries, we still have some fundamental questions that we still need to answer. And the first one is, how do we form giant planets and how do they evolve? We have various explanations for the mechanisms of formation, but we still don't know if they are, you can have, for instance, various mechanisms at play in one system at different locations, around the star or at different time scale. We don't know exactly what is the physics of accretion, when you form the planet, and this is really important on the final properties and how the planet is going to evolve. And here it's completely, related to what Matthias was saying. I mean, we need to constrain this mass luminosity relations for young planets to really be able to understand how they are formed. If we think to young Telluric planets, it's even like beyond what we're doing in terms of observations, but of course it's extremely important. Second category is more related, of course, to the atmospheres of the giant planets. How far can we go in terms of physical and spectral characterization? I think it's really important. We have been improving the capabilities of spectrographs, but still, I mean, if you just think to what we're doing now for young brown dwarfs, where we have like no problems, related to the star, we still have some limitations related to the models that we're using. We have exquisite spectra, but still the physics present in the models is a limitation, and we have to leave some degeneracy, between the physical properties, the compositions, the clouds, I mean, various aspects. So we have to stay humble, and we have to try to maximize as much as possible, the spectral coverage. For instance, we can think to GWST, that would be really nice for that. Second point is also, there is this ambitious, questions of coming back to the formations of the planets based on what you see in the atmosphere. We have to keep in mind that a lot of things is happening between the formation and what you observe at the end, of course, in terms of evolutions of the planets inside the system. So it's going to be really difficult. And then the last point is to try to explore not only the 1D, but the 3D, structure of the atmospheres. And this is going to happen. This has started, for nearby brown dwarfs, and we will going to do that, in the coming years. How precise it will be done, it's really important and difficult to say, but it's really be a very important field for the ELTs. For the atmosphere, the last point is now we are mostly limited to young, I would say, Jupiters, and I think we have to think about, what we will see with James Webb and with the ELTs in terms, of young Saturns, Neptunes, primitive Earths, and so what kind of, spectra we can expect. Third category, so more related to the demographics. So Anne-Marie was showing this nice diagram, with the masses as a function of the semi-major axis. As you can see, the diagram is not complete. We are missing a lot of parts, and this is something which is like a big, challenge for us in the coming years to fill that parts, not only in terms of masses and semi-major axis, but also considering, the properties of the stellar host, so the mass of the star, the age of the star, also the environment. And this is, I think, very important to try to understand how, planetary formations work. And one important question, I think, for us is also to try to understand how our own solar system fits into this diagram, and how it is maybe very important, this solar system architecture with like multi-belts, giant planets, Telluric planets in the inner part. How is it important actually for the emergence of life? So in terms of challenges, I'm not going to repeat much, what has been said, but yeah, we have to go closer, deeper. We have to bridge the gap with, the other techniques. There's probably also a change of paradigm, going from emitted light, so young stars, to reflected light, so older systems really nearby. And so we need to push on the instrumental concepts, the data processing, and also, of course, this must be done together with people working on theory and modeling, because we need the models. We are limited by the models just to interpret what we're seeing. I will stop here.
Awesome. Okay, we're going to move on to Trevor. So again, you have 5 to 8 minutes to summarize, but then we're going to have a discussion.
Sure. Okay.
After 5 minutes.
What's that?
I will give you a 2-minute warning after 5 minutes.
Okay. All right. So, so Andrew did a great job of explaining the difficulties associated with searching for young transiting planets. So I won't cover that in nearly as much detail, and I recommend the talk, his pre-recorded talk on YouTube. But on the right is a video showing sort of a similar thing what you saw in Andrew's talk, which is the sensitivity to different choices in your detrending methods to flattening the light curves and whether you find that planet or not. And so this is an example from the Kepler mission of a relatively young star. And this is actually one of the easier examples. And you can just see that as we change this window length, one of these parameters that Andrew was talking about, that if it's too small, you just eat your transits entirely. And if it's too large, and that's called overfitting. And if it's too large, you underfit the variability and you won't detect it through some automated method like BLS, for example. On the left, I thought it would be worth maybe talking about not just the challenges of finding the young planets, but also characterizing them and going through the hard work of confirming them, because that's a substantial part of the whole endeavor too. And I will say that I think of all the methods discussed at this workshop, I think transits is probably the easiest in terms of what we're dealing with, in terms of like the contrast between the planet signal and the star signal, the availability of the data, the availability of all these open source public tools, which are all listed on the left. It's not to say that it's easy at all, but I think we're in maybe a better place than some of these other fields, just in terms of how readily somebody like a student could get started searching for these young planets. So first, you have to find the young stars, and that has been made significantly easier with Gaia, but it's still quite a non-trivial problem. Then you can download the data. It's all public for Kepler, K2, and TESS. And then you search each star. So more so than any other method talked about in this workshop, the transit method is really only sensitive to planets that are edge on, as all the other methods don't have as strong of an observational bias. So you really have to search a large number of stars, and I think Andrew discussed that. The next parts are you have to optimize your aperture and correct for systematics, which could be due to motions of the spacecraft, variable background, breathing of the telescope. And then you want to detrend. So this is how most transit searches are done. They correct for various elements of these of the stellar and systematic noise sort of in stages, flatten the light curve, and then search for periodic signals. There are other ways you can fit some descriptive model that might encompass, say, all of the systematics, the stellar noise and spacecraft systematics. It's just more computationally expensive, but that is another method. And then you have to detect the transits. And then my advice is to just assume that it's bogus and try to kill it in every way that you can and not get excited yet. So there are plenty of ways of doing this actually from the data itself, and those are listed in the next three sort of boxes there on the left. You can, from the photometry, you can look for centroid offsets, which would indicate you might have a background eclipsing binary. You can compute the false positive probability of the transit just based on the transit shape itself. And that's because false positives, like blended eclipsing binaries, will have, in a statistical sense, will have different shapes from transits, bona fide transits, but they can be very, very similar. So this is really just a statistical type of validation technique. You can check Gaia to see if the astrometry are bad in some way, if the RV jitter is higher than you would expect for a star of that age and mass. And you also want to get follow-up data. This is, it's fine to publish a list of planet candidates from a large search. There's absolutely nothing wrong with that. But eventually somebody needs to go and confirm them. And so you want AO high-res imaging or speckle imaging. You want spectra to characterize the star. And you also want RVs to, again, show that it's not a false positive. And a follow-up transit would be great too. If you get those in different bands, you can sometimes tease out false positives that way. So a lot of eclipsing binaries will show chromatic eclipses, but transits should be achromatic. And then if it's real, that's great. And you should model the variability and the transits together and then write it up. And if it's a false positive, you just shouldn't get discouraged and search more stars. So some of the open questions, I think, within the field of young transiting planets, I think a lot could be gained not only in the search for the planets, but also just understanding more about the stars. So if we just understood the nature and the origins of stellar variability at the youngest stages. So I think star spots are reasonably well understood, but there's still more to be learned there. But at even younger ages, you see all sorts of kind of unusual variations in the light curves. And it's easy to actually find something that might be periodic or looks quasi-periodic, and you might be convinced that you're seeing a protoplanet or something crazy, and we just need to have better understanding there. And then another method that I didn't really discuss in the last slide is that you might just search all stars and then find the planets that are around stars that show rotational modulations, which indicate that they're young. And so you might just look for planets first around all stars and then try to identify the young stars later. And if you do that, you just have to be careful because stellar age determination methods don't always agree across the different methods. And so this is a notoriously difficult problem. So we can learn a lot about, transiting planets and the evolution of planets by doing better with stellar ages. Planet occurrence and survey completeness is a function of stellar age. I think Andrew may have touched upon that in his online talk. And that's something that's eminently doable today with the data that exists. We still can apply new methods and transfer knowledge from other fields to the problem of detrending, for example, or planet searches without detrending. And then once you find young planets and you're looking for correlations with planet properties and stellar age, you have to just be aware that there are going to be other correlations with stellar mass and metallicity and multiplicity, because these things are all correlated, right? And so you have to be careful that what you're claiming is an age effect is really not some effect due to something else. And then we can map the mass radius age relation, and maybe there are other parameters that matter instead of just the mass radius relationship for planets. We can understand the radius gap better, whether it's truly empty or not, and its dimensionality. And then obviously a new field that's very interesting is the observability and compositions and dynamics of young planetary atmospheres, and specifically transiting planets. And then finally, I think meaningful constraints on planet formation and evolution models from this field can be placed if we get masses, radii, mass loss rates, and eccentricities as a function of age. And also things like conditional probabilities. So the probability that you have a cold Jupiter given some super Earth, or the probability of detecting some element with some abundance in some star given some type of planet. So these types of things I think can provide real concrete constraints for planet formation evolution models.
All right. Thanks, Trevor. Okay, so let's move on to Raphael's summary, and then we'll have a discussion period afterwards. Remember, pop your questions for the speakers in the Q&A.
Hello, everyone. I'm trying to figure out which desktop I've got. Can you see my talk?
Yes.
Excellent. Okay, so I've got a very brief summary, especially that Arpita gave a really clear introduction about what the radial velocity method is, how it works. I really appreciated your talking us through how we're basically looking at the wobbling of the stars, and then we look at the spectra, and we're cross-matching the spectral lines with stationary templates, and so we can see how the spectral lines are moving as a function of wavelength. And we also obtain the cross-correlation function, which is this average spectral line. And this is really, again, Arpita detailed the two main challenges, especially for young, this is for all types of planets, but especially for young planets. The rotation of the stars is very high. So it's, a 10th of a day up to about 10 days. The stars evolve and their rotations get longer as they age. And with the radial velocity technique, with high precision, stable spectrographs, so we're talking a spectral resolution of about 100,000 ballpark, and we're looking at radial velocity precisions of about 0.5 meters per second or better, or order 1 meter per second. Really, when when we're looking at these kinds of radial velocity precisions and those kinds of small meter per second amplitudes, then we get into trouble when we're looking at stars that rotate faster than 10 days, because the spectral lines go really broad and it becomes really difficult to measure, to get that radial velocity precision. So with less than 7 to 10 days, your radial velocity precision shoots up. So you've got several meters per second precision, and that makes it much more difficult to look for your planets. This is something that I am not sure we can do very much about, but we do have an even bigger problem, which Arpita also mentioned and detailed in her talk, which is that the stars themselves, you can't consider the stars to be stationary points of light. They're big balls of plasma, and you have fluids rising up and down and moving on the surface. And all of that is interacting with strong magnetic fields, especially in young stars that have kilogauss, 100 kilogauss magnetic field strengths on their surfaces. And that is interacting with the flows, which are creating Doppler shifts. So as for example, the convection means that you've got fluids that is coming up. And so when it comes to the surface, it becomes blue shifted, but you've got flow that's coming back down inside the star that's sinking back. So that's red shifted. And so you have all these Doppler shifts. And then if you imagine on top of that, you have very large star spots. I mean, for young stars, we're talking about star spots that cover several percent of the stellar disk. And they're regions of very high magnetic fields. And so they inhibit the flow, the convection. So you have these dark areas, which is why we see these very strong modulations in the photometric light curves, as Trevor was showing us. And we also have basically that produces radial velocity variations of in young stars, you're looking at more than several meters per second. You're looking at tens of meters per second, even up to kilometers per second. So tens, hundreds, and a kilometer per second. And so these are really the two main challenges. And I've just got a very quick slide that I just want to flash just to show you that if you are looking for references about challenges and finding young planets with radial velocities, I've put a few notable references. In particular, there are a few, I've got a couple of, there's a very useful review on star spots. And this recent paper also where they're using Zeeman broadening to actually to see how much magnetic field, what the magnetic field strengths of these young stars are. And so they're measuring them directly because, as you know, magnetic fields are very elusive. And there are also a couple of recent PhD theses that have been published, and I always recommend those because they explain things in a lot of detail and they're very didactic. So I've got just a couple of open questions to get the discussion going. There have been great questions in the chat. The first one is and to echo Trevor's point about, we need to understand what the stars are doing, because that is how we're going to go from, oh, there's this intrinsically driven noise in our light curve or in our radial velocity curve, and we don't understand it, to we have a signal and we can model it. So we need to understand what drives the intrinsic variability of the host stars. And perhaps we can, well, we need to develop physically motivated models, and maybe we can identify reliable indicators of activity, as Arpita was saying. And therefore, how can we best account for intrinsic variability in radial velocity analyses? And as echoed, Gail mentioned it, and Anne-Marie, and many people, how can we get together to have more overlap, so overlap in contemporaneous observations and also looking at the same targets, right, with different observational techniques. And this is particularly important when we're looking at radial velocity observations. And planets detected by with radio velocity observations, because if you see a signal in radio velocity, and even if it appears to be coherent over the length of your data set, and maybe you have 10 years of data and you have excellent sampling, right? And so it looks coherent, it looks periodic, but it still doesn't tell you what the nature of the signal is, right? You don't know if the signal is really caused by a planet. And in fact, we don't know enough about the stellar variability to really be able to say, oh, this signal has been coherent and periodic over the last 10 years. So it must be a planet. You know, we don't know enough about stellar variability to say that today. So we really need independent detections from different observational techniques. And I will stop here. Thank you.
All right, great. So we can move on to discussion. So kind of going from that idea of combining the techniques, I guess for our panelists, what do you think about how can you combine the different techniques to potentially overcome the challenges that each individual technique faces? Like how is the combination of the sum of the parts, how is it greater than the individuals?
Maybe I can start with something that I mentioned in the chat, which is that the transit technique can really help. So we've seen these plots with the rotational modulation of the stars, and that in young stars that are very active, that are dominated by star spots, that can tell you about the rotation period of the star, which is actually a great plus, because when you're looking at older stars, often we're not sure what the rotation period of the star is, and so that's a big obstacle, because once you know it, you can eliminate if you have signals in radio velocities that are the rotation period or the harmonics, you know it's not a planet, right? I mean, there could be a planet there, but you can tell its activity, and you can also learn about the active region lifetimes, which are also important, to know if you know when to expect the coherence of the activity signals to go away. So that can be really important for radio velocities. And as we get more better coverage sampling with radio velocities, hopefully we can use the radio velocities to feed back into the transit data as well, so that you can isolate your transits as well.
Yeah. So, I mean, it seems like radial velocity and transit are very coupled together in many ways, especially in terms of being dependent on understanding the variability of the star. So it seems like there's a lot of techniques that are shared between the two. So I guess the question for Raphael and Trevor would be like, how does that work in terms of that synergy? How from the either end are you tackling the issue of stellar variability? And then for Gael, will this eventually be a problem for direct imaging? I guess right now we're looking for giant planets around bright young stars, but when we start trying to look for higher contrast, lower mass planets, will stellar variability become an issue for that?
Well, yeah, I mean, for direct imaging and astrometry, I mean, I think we are not in the same dimensions than, transit and radial velocity. So, yeah, so far it has not been an issue at all. But yeah, I mean, we have to think a bit more in detail, and particularly, when you want to get to very, high contrast, precision. Yeah, you have to think maybe a bit more about that. But it's not, yeah, nothing, comparable to what you have, to the issue you have for transit and radial velocity, of course.
I'm wondering if it's going to end up being a problem for, HabEx and LUVAR and the next generation of direct imaging surveys, because you're going to have, what, 10 to the -9 contrast?
Well, I mean, I think that's a tough question. So maybe I don't have, all the background to answer. But I mean, it's really depending, I think, on the time of the observations that you're doing. Currently, we are doing, relatively short observations, in high contrast imaging. It's like 1 hour, on the target. So, but then when you start to think yet, maybe you want to spend like, you know, I don't know, 100 hours on one target, then it's another story. And it can be, of course, a limitation. So currently that's not the case, but yeah, probably we have to start considering that for the future.
Actually, I mean, I don't want to sound depressing, but you were talking about how we need to move from emitted light to reflected light, which is, yeah, totally fascinating, the reflected light stuff. And I'm pretty sure that in reflected light, we're starting to have problems like having to take into account the stellar variability.
Sure, but I think it's also related to the time scale of the events that you might have, and yeah, and your observing strategy. But yes.
And
Yeah.
some stellar variability timescales are pretty similar to the rotation periods we expect for directly imaged exoplanets, which may be an issue eventually.
Yeah.
Yeah, okay, so going back to the synergy in particular between RV and transit in terms of removing stellar noises as one of the particular challenges, we have a question from the Q&A about whether machine learning methods and algorithms have been used for that, for transit and radial velocity detections, and well, just in general.
Well, I know that machine learning has been applied to the problems of finding transiting planets. And it's maybe less of a question of like which algorithms and more about how you're doing it. So some methods have focused on recognizing what a phase folded transit looks like. But other methods might try to model the entire light curve. So I think there are many ways to do this, and the point I was trying to make really is that it's relatively underexplored. So I wouldn't say that it necessarily has to be your first step, because, you know, as I think Daniel pointed out, that many methods that we have already do pretty well, but it's always interesting to pursue a new method, and you learn a lot about its even when it's failing in some ways. And so it's all part of sort of working towards getting to the best methods. And inevitably, some methods do well in some regimes and others do better in other regimes.
Cool.
So
Okay.
Oh,
go ahead.
Oh, right. Yeah, in radial velocities, I just wanted to add briefly that we are starting to use machine learning. So there's the moving averages, Gaussian process regression. There is even some neural networks that are starting to be used for for looking at radial velocities of our own sun. So we have a lot more data and a lot better sampling, and it's a little bit different in that respect. And I do think that ultimately the solution will be in combining forces, you know, between the power of machine learning and also our physical understanding of what's going on the surfaces of the host stars, right? And so when using, I'm very excited about machine learning, and I encourage you to go for it because they're really versatile tools, right? If you want to pick up a machine learning technique. And at the same time, I encourage you to remember that the machine learning will not tell you the difference, you know, it will not tell you about the signal, the nature of the signal. It tells you about the statistical significance of your signal, which it's important, but it doesn't actually tell you, you know, is it a planet? Is it an instrumental systematic? Is it stellar variability?
I mean, best maybe I can add for direct imaging. I mean, it's a bit the same. I mean, for the past years, I mean, we have not been using machine learning technique, but it's starting. And all these questions of what you're detecting, and if you could use, you know, alternative methods just to be sure, you know, of exploiting as much as possible, you know, your observations. It's starting now.
I guess an adjunct to that with machine learning, you usually need a large enough training data set, right? And so some of the question is having that data set, and certainly with transits, with things like TESS and Kepler, you certainly now have those data sets available.
Definitely. But again, I mean, I agree with everything that Raphael said. Again, I think it comes down to, how you're building your model also. Like, don't underestimate sort of the beginning stages of approaching a problem and the decisions you're making in the very beginning.
Mhm. Yeah.
Cool. Okay, so a question from actually one of the other panelists, from Laura Perez, who couldn't put it on the Q&A because panelists can't. We've been talking about the synergy between radial velocity and transit and direct imaging. What about the synergy between ALMA techniques and specifically direct imaging, or any of the other techniques?
Well, I mean, for ALMA and direct imaging, I mean, it's there. I mean, we have seen that for disk. You have some detection for planets, with ALMA, is this like a Keplerian kick, and we are looking for the planets, in direct imaging. So we don't have, I think, for the moment, like a clear confirmations, of one planet detected by ALMA and confirmed, in direct imaging, but it will come. Or, I mean, possibly PDS-70, I think, is PDS-70 B and C. I mean, you have some deviation that you can see in the Keplerian motion. Maybe that's the first one.
Yes, in fact, Laura wrote on the chat to the panelists exactly that, PDS.
Okay, good.
Yes, very interesting object. All right, cool. I'm just trying to find other questions from the chat. I have a few more myself. But another one regarding stellar activity, especially as the main thing that's an issue for RV in transit. How do higher cadence and longer time baseline observations help with this? Like, what sort of cadences and time scales do you really need to be observing things to be able to beat that down?
So I will jump on this question and say, for radial velocities, the fact is that we don't actually really know exactly what the optimum observing cadence and strategy is. And so this is why we actually recently, if you're very interested in radial velocities and EPRV, extreme precision radial velocities, I encourage you to check out. We have a report coming out very soon that was a group of experts worldwide. Arpita and I were part of this, and many others on the call, where we basically, NASA and the US National Science Foundation asked us to design a decadal map, of how we're going to reach Earth mass planets in the habitable zones around sun-like stars. So it's slightly different because they're much older stars, but many of the issues are the same, and the stellar variability issues are certainly very similar. And in there, we recommended that actually you should take a point every night. You should take the highest cadence that you can, because that might be what we need. In fact, you might need several points per night if you want to constrain the granulation, for example, which operates at several hours timescales. But well, that's several points a night. That's becoming unreasonable logistically. But I mean, you can always downgrade later. So for example, with the terra hunting experiment, which the University of Exeter, where I'm at, is a major partner in, it's led by the University of Cambridge in the UK. It's a 10-year survey. So we're going to get that 10-year baseline, which is approximately one magnetic cycle of the sun, right? So it's targeting old sun-like stars again, but we are going to be taking we're going to endeavor to take a point every observable night, because we just don't know what's the ideal. Trevor, did you want to add anything?
I fully agree. Cadence is really important. I mean, going back a little bit to the discussion of the synergy between transits and RVs, I think it's really important to try and get contemporaneous photometry in RVs as much as possible. And also, if you are a student that is working on stellar activity and mapping, variations in RVs to photometry and vice versa, that's a very cool and important thing to be working on. So it's not, I know a lot of people want to be planet hunting, but a lot of people in our community will be modeling RVs and transits and stellar variations, and not always doing it the best way. And so the purpose of some of these stellar activity investigations is to assess how good our assumptions are. And you know, for anybody that sits on tax, like giving time to these stellar activity experiments, I think, is important, especially at super high cadence. And you might not need to do that many of them before you learn a lot.
It's all about the stars.
Right.
So yeah, actually, Lynn Hillenbrand just chatted to the panelists that someone should mention that stars are interesting on their own. Not everything needs to be in service of planets, and I think that's a very fair comment. Okay, so we should start drawing to a close, but I had actually kind of a question for all of the panelists, which is, what can you learn first of all about demographics of planets by combining detections from all of these different techniques, and what can you characterize about exoplanets specifically by combining these techniques?
Maybe the most exciting thing from combining all the techniques is that we're going to be able to look at the planetary systems as a whole, so at a range of orbital periods, and not only in space but also in time, right? Because with the direct imaging in particular, we're getting a look at the young stars, and then with the transit and radial velocities, we're also looking a lot in the older regime, and so we're adding that time dimension.
Yeah, I mean, ideally, I would like to have is like, you know, a complete view, you know, with the evolution of the planetary system, and to really see what is, you know, the architecture at the formation level, and then the dynamical evolution. I mean, that would be extremely important for us. And when I was speaking, for instance, about, you know, the solar system architecture, we know that, you know, Jupiter's from at one place and moved, and it changed completely, you know, the landscape for the telluric planets. So having that for all, you know, the planetary systems in the sky would be like amazing. And of course, it has to go through the synergies of the techniques. We have to. There is no ways to go there. No other ways to go there.
Yeah, I related to this issue. I had a question in one of the breakfasts that was along the lines of, why is it so important to have overlap between different methods? And I think part of the reason is because we can't necessarily just trust the results from one method alone, because that requires really understanding survey sensitivity and all these complicated things. And so different methods should agree with one another. And if they don't, something's wrong with maybe the analysis or something like that. Or there's a bias in the samples, and you have to understand that. And then part of the reason I was sort of highlighting the conditional probability issue in the summary slide or open question slide was because, you know, it's fine to detect like 50% of sun-like stars have some super Earth and sub-Neptune, and then it's fine to build models to recreate those. But a much harder challenge for theorists is to also recreate those in the same systems that say like 10% of the time have a Jupiter or something. So understanding which planets occur with which other planets will actually provide you know, a much narrower sort of needle to thread for the theorists.